Okay, second video over the kinematics. Hopefully I can get it done before I have to start teaching again. But let's go through this example, and then there's a quick one at the end. Particle moves along a horizontal line so that its position given by this function s of t, and it specifically tells you to use a calculator. The reason why, I don't need the calculator to get the velocity formula, taking the derivative is easy, but the derivative is not going to factor. So instead of using the quadratic formula, you'll get to use a calculator. All right, let's go get the velocity. Remember, moving right is when the velocity is positive. Moving left is when the velocity is negative. And then at left, it didn't even ask for at rest, so that's good. Let's go get the velocity formula. 3t squared minus 5t plus 2. Again, the same domain restriction would apply. And then if it would a factor, then you could do it just like we did on the previous example in the last video. But since this doesn't factor, we're just going to use the calculator to graph it. Right? So use my graphing data calculator to graph. And then let's get a good sketch of this function. I already have it typed in. You can see here on my calculator, I have the original typed in, which we're going to need it in a minute. But I have that graph turned off. I have the derivative typed in. And then here is the graph. Of course, it's a parabola. It's going to have an intercept of 2. So it starts off above, and then it's going to dip down below, and then do something more or less like this. There's your velocity graph. Okay, so I'm going to turn this off, and then let's go. I guess I'm going to need it here in a second. When is the particle moving to the right? We know your particle would be moving to the right when the velocity is positive. So that's going to happen when this velocity graph is above the x-axis. So this interval from 0 to this point. So I'm going to need to know what that intercept is. And then also from this point, so I need to know what that intercept to infinity. Obviously that's 0, but let's go find this intercept. And then we'll go find this intercept. And then we'll be able to answer these questions. Let's go back to the graph. Second, trace. And we need the x-intercept, so 2. Let's do the first one first. Left bound, right bound, guess. Here we go. So we got this as 0.21, I'm going to say 0.213. You can either round or you can truncate. I'm just going to say 0.213. And then I'm going to actually store that value. So I want to make sure that I quit out of the graph. Then I'm going to hit X. And then store, which is right above the on, stow, then alpha A. So I'm going to store that value so that if I need it later, which we will, we're not going to use the rounded value, right? We're going to use the precise stored value. But instead of having to write down that decimal, I'm just going to store it and have the calculator save it for me. Okay, let's go get the other intercept. Second trace 2, left bound, right bound, guess. And then here we go, 3 point, let's do 119. And I'm going to store that one in B. Again, truncation is when you just read the first 3 and then you just truncate. So you just end, right? You don't even bother looking at the 4th. You can either use the 4th to round the 3rd. Obviously, that's rounding. Make sure if it's 5 and up, you round up. If it's less than the 5, you would round it down. So you can use the 4th decimal spot to round the 3rd, or you can truncate, which means you just straight up ignore everything past the 3rd. Either way is fine. The AP exam accepts both truncation with a C, not a P, truncation, and then a rounding. I'm going to go snag that one too. So we got X. So it's taking the X value, wherever that cursor is, it's going to take the X coordinate of that point, and I'm going to store this one to alpha B, just so that I have those later. Okay, so that's great. Let's answer the questions. Particle is moving right when the velocity is positive. So from 0 to this first intercept, 0.213, parenthesis there, but at 0, the point is positive, right? At 0, the graph is above the x-axis. So I could include that, and you should include it. And union this intercept to infinity, so 3.119 to infinity. Okay, let's do left. Moving left when your velocity is less than 0, so that's going to be between the two x-intercepts when this graph is beneath the x-axis, so 0.213 to 3.119. Okay, and if it would have asked for at rest, you would say it's at rest when the velocity is equal to 0, which would happen at this time and at this time. Okay, here we go. Distance traveled by the particle. Remember your distance traveled. This particle, it starts off moving to the right. So at time equals 0, I don't know what the location is yet, but it moves to the right. Then at time equals 0.213, it stops, and then it's going to come back to the left. And then at the time equals 3.119, it turns and it goes back to the right. And then we're going to see, hey, at time equals 5. We need to know what the locations are at all of those different moments, right? So I'm going to make this table, t-values, and the positions of all of those t-values. So I'm going to go back and I'm going to take 0, plug it into your position. That's easy. I can do that one in my head. That's -3. So it starts off, if you're thinking about your number line, it starts off at time equals 0 at -3. Then it's going to go to the right, then back to the left, then back to the right. So we need to figure out what are these other values so I know how far to the right, how far to the left, and then how far to the right in that last leg. But you always need the final and the initial position. So let's go get this. If you were to plug it in, remember I already have the original function, the position, typed into y1. So I could do vars, y vars, 0. Of course, that was the initial position. I can also just plug that in my head, pretty easy. And then we would take the function, plug in 5. So the final position is at 7. Okay, then let's go do the other ones. Now, I need the locations where it turns. So that's your 0.213 and that's your 3.119. Now, you don't want to ever use a rounded solution. So don't use this. You'd want to use that exact decimal, which I had stored in A and I had stored in B for the second one. Okay, so I'm going to go take this, and then you could do vars, scroll to the right, y vars, we're in function mode. Then I'm just going to tell it, hey, alpha A, I'm going to have that function evaluate, but at that precise decimal, not at the rounded number. So then we get -2.791. So it didn't go very far, right? It starts at -3, and then it's -2.791. It doesn't go very far to the right, because look at the time interval. It wasn't going to the right for very long. And then let's see, that's almost 3 full seconds. So I'm kind of thinking this distance to the left is going to be more significant. But let's go take this, and let's go evaluate it with alpha B instead. Ooh, -15. Yes, there we have, -15.06. Again, you can round or you can truncate either way. So I've got all the locations of all those moments. Okay, so picking back up, we have the locations at all those points. Let's go now find the change in the positions. Let's figure out how far this particle travels in each leg of those journeys. So it starts at -3 and it goes to -2.791. So you just take the second position minus the first. So -2.791 minus -3, 0.209 plus 0.209. So how far did I go to the right? 0.209. Again, the positive just means that it went to the right. Then let's take this minus this, and that's going to tell me the distance of this second leg. So -15.06 minus -2.791. So it looks like it went 12.269. There's no units on this, so just -12.269 to the left. Again, the negative means left. And then from the -15 to the 7, let's figure out how far we go during that third interval. So you take the final position minus that one right before it, and that's going to give you 22.06. So I find all the positions, then I do this minus this, first change, third minus the second, there's your second change, fourth minus the third. So you need to find all your change in your positions. Now if I added these numbers together as they stand, if I did 0.209 plus -12.269 plus 22.06, if I counted the negatives as negative, it's going to cancel out with some of the stuff that was positive. And what you're going to end up with, 10, that's your displacement. right? When you count the distance to the right as positive, and if you count the distance to the left as negative, they're going to cancel out, and you'll end up with the net change in your distance, which is your displacement, which is useful. And sometimes you have questions that want the displacement. But here we didn't. We wanted the total distance. And again, the displacement you could have just found by taking the final minus the initial. We know if this is -3 and that's 7, I know that net change between them is 10. If I want the total distance, I need to disregard any negatives. So I find the change in the positions, and I'm just going to add them all together, ignoring any negatives when they come up. So 12.269 and 22.06. So I'm going to go back, and then instead of this one, instead of that 12 being a negative, I'm just going to delete it. Make sure you count all the individual distances for all those individual legs. Make sure you count them all as positive. And then I can get the total distance traveled is 34.538. There's no units for this, so you can just put the number. If there's no units in your question, then you don't need units on your answer. Okay, again, the displacement would be 10. Displacement, it's final minus the initial, or if you would have counted that as negative, you would have also gotten the displacement. But if you want the total distance, you've got to figure out what are all the important times, what are the locations at all those times, and then you have to do the change in the position and then disregard the negatives if and when they come up. Okay, so now let's do speed is increasing. Speed is increasing, that's the same thing as saying speeding up. Speed decreasing is the same thing as slowing down. Okay, so if your speed is increasing, that means your velocity is getting larger. Getting larger in size, right? Speed is just the magnitude, it's the size of your velocity. So let's again think about this graph. And we're going to answer this one graphically. I'm going to redraw the velocity for us, even though it's up above. That starts off here. We know that's at 0. I know this is at 0.213. I know this is at 3.119. Remember, I had that stored in alpha A. I had this stored in alpha B. We're going to also need to figure out where this minimum is, because speeding up, that's where your speed is increasing. That's where your velocity is getting larger in size. Another way to think about that is your velocity graph is moving away from the x-axis. Right, the x-axis is 0. It's a size of 0. So if the graph is either moving upwards in a way, that means, hey, it's positive and it's becoming a bigger positive number. That means the size is getting bigger. Or if the graph is negative, but moving away from the x-axis, like maybe here the y-coordinate is a negative 0.2, maybe here it's like a -1, here it's like a -4, who knows, right? But if your graph is moving away from the x-axis, either in the negative direction or in the positive direction, the x-axis is the size of 0. And if you're moving away from 0, that means the size of the number is getting bigger. Even if these are getting bigger negative numbers, that's still a bigger size, right? -2 has a bigger size than like a -0.2. So moving away from the x-axis, that means the size of the number is getting larger, which is an equally good way to get speeding up. Okay, so speed is increasing, speeding up, those are the same. You could think about when both the velocity and the acceleration have the same sign, or if you have the graph of the velocity, it's when it's moving away from the x-axis. So that would be from this intercept to the minimum, which I need to go find, and from your second x-intercept to infinity. Now let's go back to the graph and let's get that minimum. So second trace minimum is 3, the left bound, right bound, and then the guess doesn't really matter. So it looks like that minimum is at 1.666. Looks like 1 2/3. So we could go 1.666, and there you have it. There would be your speeding up. Speeding up, aka speed is increasing. If you want to think about the velocity and the acceleration having the same side, that's okay. But you can also think about, hey, is the velocity, is it moving away from 0? Is it moving away from the x-axis, aka getting bigger? Or is it coming back towards the x-axis? Let's do slowing down. Okay, so speed decreasing. That would be the same thing as saying slowing down. That would be the same thing as saying your velocity is getting smaller in size, which would mean your velocity graph, it's not moving away from the x-axis, it would be approaching, getting closer to, approaches the x-axis. The x-axis is a size of 0. So if your graph is coming back towards 0, like if it's positive and getting closer to 0, that means it's getting smaller and smaller and smaller, right? It's getting smaller in size. Or if you have a big negative number, and if your graph is getting closer to 0, as you get closer to 0, you have smaller negative numbers, right? The size of the number. You think about the distance from 0. 0 is the x-axis. So speeding up will be moving away from the x-axis, moving away from 0. And then slowing down would be when it's coming back towards the x-axis. So slowing down would be from 0 to the first intercept. And then it would be from the minimum to the other intercept. Okay, now this one didn't ask for slowing down, aka speed decreasing, but you could have done it just as well. Now let's also think about another important conceptual thing. This is the graph of your velocity. We could kind of see the acceleration from it. So this first interval from 0 to your 0.213, 0.213 to your minimum, and then your minimum to the second intercept, and then from the second intercept to infinity. Let's think if we can determine the combination between your velocity and acceleration. Let's see, this first interval is going to be this part of the graph, right? Now that graph, right, this is the velocity graph, right? And this little part of the graph, it's above the x-axis, so I know the velocity is positive. But this little part of the graph has a negative slope, so I know the acceleration, aka the derivative of the velocity, must be negative. So because this part is above, the velocity is positive, but since it has a negative slope, I know the acceleration is negative. And remember, when the two signs are different, that would be a slowing down, a speed decreasing interval. Let's look at the next chunk, right, which would be this piece of the graph. Since this little segment of the graph is beneath the x-axis, your velocity is negative. And then the slope of this part of the graph is negative. Therefore, your acceleration is negative. But if both of the two things, the velocity and acceleration, if both of them are negative, that's going to be speeding up. It's speeding up in the negative direction, but it's still speeding up. This third interval, the velocity is negative since this graph is below, but now this graph has a positive slope. So your acceleration would be positive. So this interval, since they're different signs, that would be a slowing down. And then this last interval, the graph is above, therefore the velocity is positive, and it's got a positive slope. So that would be your plus speeding up. So you could kind of think about it like this. It's kind of similar to how we did some curve sketching stuff from a previous notes packet. Remember, the location above or below will tell you the first thing, right? It'll tell you whether the velocity is positive or negative. But then the slope of this function will tell you the acceleration and whether it's positive or negative. And then you could think, hey, when they're the same, that's speeding up. When they're different, that's slowing down. But I think it may just be easier for you to remember if the graph of the velocity has to be the velocity. It's not the graph of the position. It's not the graph of the velocity, the acceleration. It has to be the graph of the velocity. 0 is the x-axis. So if you're moving away from 0, either upwards in a way or downwards in a way, if you move away from the x-axis, the size of your coordinate, the size of your y-coordinate is getting bigger. It may be getting bigger in the negative direction. That just means you're moving faster to the left. But moving away from the x-axis, that would be speeding up. Moving back towards the x-axis, that's when you're getting closer to 0. That would be slowing down. So a couple different ways. You can do the sign charts and figure out when they're the same, when they're different. Or if you have the graph of the velocity, or you have a calculator, and then can get the graph of the velocity, moving away is speeding up, moving back towards is slowing down. So a couple different ways to do speeding up, slowing down. Hopefully it makes sense. One more question today, very quickly, and then we'll be done. Multiple choice, how lovely. And it's a calculator question. You can tell by the really ugly decimals, right? So here we go. I'm going to clear my calculator. A particle moves along the x-axis so that at any time greater than 0, it's velocity. So it gives me the velocity formula. Watch out, you're in trig, so make sure your calculator is in radian mode. We have the velocity formula, and it asks for the acceleration. Well, I know the acceleration would just be the derivative of the velocity. Could I take this derivative myself? Sure, you would need to use chain rule. But since we're going to use the calculator, let's just use the calculator. Let's take the derivative of this velocity formula, and then specifically, we're going to evaluate it at time equals 4. And we're going to use math 8 in my graphing data calculator. So let's go type this in. Well, you don't have to. Let's just do math 8. That's how you can do derivatives in the calculator. The variable button is x. Let's type it in. 3 plus 4.1 cosine 0.9x. And then, oh, that's it. And then let's see, we need to tell this to evaluate at 4. So we're having the calculator do the derivative for me, and it looks like it gives me the 1.633. So it rounded, it didn't truncate. That's okay. If this was a multiple choice, they would accept either the 0.633, that's rounding, or they would accept the 0.632. They would accept both. Okay, so that one we could have done by hand, right? I could have manually found the acceleration. Let's see, the derivative of that's 0. The derivative of this, you'd have the derivative of cosine is a negative sine. And then you would have the 4.1, and then you could just take that and multiply by 0.9. That's because of your chain rule. And if I took the derivative, let's see, we have the negative 4.1 times 0.9. So you have this function is negative 3.69 sine of 0.9t. If I actually take the derivative myself, all I would need to do is evaluate the function. Negative 3.69 sine, then I had 0.9 times 4. And then you would get the same thing. So you can either manually take the derivative, and then all you would have to do is evaluate it, or if you want the calculator to do the derivative for you, that's what the Math 8 feature. But there you have it. Pretty easy multiple choice to finish this kinematics.